Hi. Today, we're going to build a ridge regression algorithm from scratch. We'll start out with an overview of the algorithm and some of the theory. Then we'll implement it in Python, and then we'll evaluate how well our model works. Ridge regression is a form of linear regression where we plot points and then draw a best fit line to try to approximate those points. And with the line, we can make predictions about the future. The equation for the line is y equals b0 plus b1x. And if you're not familiar with the equation, I did a previous video about linear regression where it's explained in a lot more detail. But to give you the overview, b0 here is the y-intercept, b1 is the slope of the line, and the x coefficient, and y hat is the predicted y. So we can use the line to get predictions given our x values. Ridge regression adds another parameter called lambda, which is the ridge penalty. And let's take a look and see what that penalty does. So as we start to increase our penalty, we can see how our b1 coefficient changes. And we can see it actually starts to shrink as we increase our ridge penalty. And eventually the line becomes flat, and b1 is very, very close to 0. What we can say is that as the penalty lambda increases, the y-intercept stays constant, and the coefficient b1 goes to 0. Now let's talk about why we want that and why it's useful. So lambda helps us handle something called collinearity by penalizing b1 and other coefficients. Now let's talk a little bit about collinearity and just set up some of the intuition around ridge regression. Let's say we want to predict something about the Olympics. Specifically, given how many athletes a country enters into the Olympics, can we predict how many medals the country will earn? We can use this data table to do that. Each row in this table is a country's entry into the Olympics, and we have columns indicating how many athletes they enter and how many medals they won. Now, in linear regression, we can actually plot these points onto an axis, where x is the athletes and y is the medals. And we can plot a few more points that aren't shown but are in the larger data set. And then we can draw a line that fits these points. And this is a linear regression line. And in this case, our b1 coefficient for athletes is 0.2. That's the slope of the line. And intuitively, what that coefficient means is that if we enter one athlete into the Olympics, we expect to win zero point 0.2 medals. So if your country enters 5 athletes into the Olympics, you'd expect to win 1 medal. If your country enters 10 athletes, you'd expect to win 2 medals, and so on. And that's how we interpret the linear regression line. Now, let's say we want to add one more predictor. Let's say we want to use both the number of athletes a country enters into the Olympics and the number of events they compete in to predict medals. So when you enter into the Olympics, you enter your athletes into a certain event. So events would be something like judo or basketball. We could add an extra column to our data that indicates the number of events the country entered into. So we now have 2 columns, athletes and events. And before we go ahead and predict medals, we can actually plot these columns against each other to check if they are collinear. So here we have athletes on the x-axis and events on the y-axis. And we can plot them. And then we can do something similar to what we did last time and actually draw a line to approximate the shape of the data. And when we draw this line, we see that it fits the data very well. And our data is actually collinear, which means that our 2 columns, athletes and events, are highly correlated. And if you're familiar with the R value from a linear regression tutorial, the R value here is 0.96, which is a very high R value. That means that these 2 columns are basically completely related. So as athletes increases, events also increases. And that makes sense. When you enter more athletes into the Olympics, you have to enter them in new events. You can't enter 100 athletes into one event. You have to enter them into different events. And when we run our linear regression, we find that our athlete coefficient B1 is 0.5, and our event coefficient B2 is negative 0.7. And intuitively, what this means is that for every athlete we enter into the Olympics, we expect to win zero point 0.5 medals. But for every event our country enters into, we expect to lose medals, which doesn't make intuitive sense, right? So if your country enters more events, you would expect to actually win more medals because your country has more chances to win medals the more events it enters into. What's happening here is that since athletes and events are collinear, the coefficients are becoming skewed. So the medal coefficient has increased beyond what you would expect if you were only using athletes to predict medals. And in order to compensate, the events coefficient has decreased to be negative. So when you subtract these two out, when you add these two and get the final medal count, it'll be correct because we're over indexing on athletes and then removing our events, which is not at all intuitive and not how this should work. And this is happening because athletes and events are so highly correlated and collinear. And linear regression can't deal well with collinear variables. And what happens here is your linear regression line will look great when you're training. So on your training data, it'll look really, really good. But then when you go to make predictions on future data, you'll find that your future data points don't quite fit the line. And this happens because your algorithm is basically fitting to small quirks of your training data set and not learning the underlying system that governs how athletes are related to medals. So your model will look great in training and not so great when you go to predict things in the future. Now, what we can do here to fix that is to apply the ridge penalty. And let's take a look at how the ridge penalty shifts the coefficients. So we start out with a B1 of 0.5, that's our athlete coefficient, and a B2 of negative 0.73, that's our events coefficient. Now let's increase the ridge penalty and see what happens. So we can see that our B1 and B2 start moving towards 0 as we start to increase our ridge penalty lambda. And eventually what happens is we get close to the B1 of just running a linear regression on the athlete's variable alone. So this makes a lot more sense, right? There's no negative value anymore. We have smaller coefficients, and these coefficients are no longer overfitting. But what happens when you increase lambda too much is you start underfitting the data. So the coefficients get too small, and you're no longer making good predictions because you're not fully fitting the data. So you want to pick a lambda value that doesn't overfit the data, but also doesn't underfit the data. And we'll talk about that later. But the important thing to know now is that the ridge penalty helps us correct the coefficients so they make more sense intuitively and they help us not overfit. As I mentioned, the ridge penalty reduces overfitting when predictor variables are collinear. Now let's dive into how we can actually apply the ridge penalty. You may remember, if you've studied linear regression or you watched the previous video, that we can represent our points as a set of matrices. So y, which is our medal counts, equal x, which is the number of athletes and the number of events, times b, which just represents our coefficients. So y equals x times b. And matrix multiplication works a little bit differently from normal multiplication. And we'll talk a little bit about that later, but I would encourage you to watch the linear regression video if you want to know exactly how this equation works. Then we can write this equation as y equals xb, and then we can actually solve for b. So the first thing we do is we multiply both sides by x transpose, because what we want to do is invert the matrix and get rid of everything on the b side that's not b. So we multiply both sides by x transpose to get a square matrix that we can invert. Then we invert the xtx term on both sides, and then we're able to cancel out the xtx times xtx inverse on the b side, and we end up with this equation. B equals x transpose x inverse times x transpose times y. And I would encourage you to watch the linear regression video if you're not familiar with this or you want to know more about it. But we can keep going even if it's not 100% clear how that worked. The key part of the equation is the part highlighted in purple, x transpose times x inverse. And this is the place where we actually apply the ridge penalty. So let's dive a little bit deeper. So x transpose is the x matrix turned to the right. So you can see in the x matrix, the leftmost column represents our y-intercept. The middle column represents our number of athletes, and the rightmost column represents the number of events those athletes competed in. In the x transpose matrix, those are turned to be the rows. So the first row represents the y-intercept, the middle row represents the number of athletes, and the last row represents the number of events. And when we multiply these out, we get a matrix x transpose x, which is what we call a square matrix that has the same number of rows and columns. So when you do matrix multiplication, your final result has the same number of rows as the first matrix you multiply, and the same number of columns as the second matrix you multiply. So multiplying x transpose times x always gives you a square matrix. And the nice thing about a square matrix is we can actually invert it. So the inverse of x transpose x is shown on the right. I'm not going to get deeply into matrix inversion here, but again, I recommend watching the linear regression video if you want to know more about it. And this is where we add the ridge penalty inside the part before the inverse. And in here, lambda is our ridge penalty, and I is the identity matrix. And I'll show you what that looks like when we apply the ridge penalty. So here's our x transpose x matrix. And then what we do is we add lambda times the identity matrix. It's not quite the identity matrix. You'll notice the cell at the top left is 0, when in the true identity matrix it would be 1. And this is because we don't want to penalize the y-intercept. It's a common convention not to penalize the y-intercept. You can penalize the y-intercept if you want to, but most implementations of ridge regression don't. So we set that to 0 so we don't penalize the y-intercept, and we only penalize our athletes coefficient b1 and our events coefficient b2. So when we multiply lambda by the identity matrix, we get our penalties for b1 and b2. So you see that represented there. And then both of these matrices are the same size, so we can actually just add them together. And let's take a look at that. So you'll see the addition basically adds each element together. Okay, so we took a look at where we apply the ridge penalty. Now let's look at one other case when you would want to use ridge regression. So let's say you have two columns in your data set, and one of the columns is just a multiple of another column. So in this case, athletes 2 is just 2 times the athletes column. And this may look kind of strange. You're maybe wondering why this would happen. But sometimes when you have hundreds or thousands of variables you're using to predict, you can get accidents where one is a multiple of another, or maybe when you were measuring them, you collected a multiple for some reason. So this is more common than you think. And when columns are what's called combinations of each other like this, our x transpose x matrix actually cannot be inverted because it's what's called a singular matrix. So the key thing to remember here is that our columns, if they are just multiples of each other, or they are other columns added together, like if we had one column that was athletes plus events, or a column that's athletes times 2, that matrix, that resulting XTX matrix, cannot be inverted. But when we add in the ridge penalty, it can be inverted. So this is another case where the ridge penalty can be useful. So the two cases where ridge regression is useful are in reducing overfitting due to collinearity and enabling matrix inversion when one of your columns is just a multiple of another column. And we can take a look at our full ridge regression equation here. So B, which represents our coefficients, equals x transpose times x plus lambda times the identity matrix, the inverse of all that, times x transpose times y. and that will give us our coefficients. And there's one thing we need to do before we just solve for this equation. We actually need to standardize our data. And what that means is we need to set the standard deviation of our data to 1 and the mean to 0. And we do that by subtracting the mean from each column and dividing each column by the standard deviation. And the reason we do this is if we take a look at athletes and events and we look at these values, we can see they're quite large, right? And then when we look at our lambda term, if our lambda is 2 or 5, that lambda term is on a different scale, right? It's much smaller. What we want is our lambda to be about on the same scale as our columns. So we just standardized our athletes and events columns, and you can see these values are much smaller. And then if we were to go to another data set and apply a similar lambda, we would get similar results. Whereas if we're using the raw numbers without standardization, we would have to have very different lambda values depending on the actual numbers that we are using to predict. So standardizing the data ensures that we can keep a relatively consistent lambda value across different ridge regression predictions that we do. And you can see here, this is the xt times x matrix for our standardized athletes and events. And this is lambda times the identity matrix. And you can see that they're approximately on the same scale. The lambda term isn't tiny compared to the xt times x numbers. Okay, so we've now learned the theory of ridge regression. Let's dive in and implement this in Python. Then the next thing we're going to do is import NumPy as NP. And NumPy is a Python library that lets us do some linear algebra. So some of the parts of the equation, we will be using NumPy to help us solve. Then we're going to import a part of scikit-learn. Scikit-learn is a Python machine learning library, and we're going to use one of its utilities to just help us out. The first thing we'll do is we'll read in our data using pandas, and we'll read it into a pandas data frame. So let's go ahead and run that. And then we can take a look at our team's data frame. So each row in this data frame represents a country's entry into the Olympics. And you can see we have the athletes, events, and medals columns. Those are the ones we're going to be using. And you can see we have 2014 rows. So that means we have 2014 individual entries into the Olympics. We're going to split our data up into train and test sets using the train test split utility from scikit-learn. And we'll take 20% of our data into our test set and 80% into our train set. And this is going to let us evaluate how good our algorithm is using the test set. So once we train it on the train set, we'll evaluate its error on the test set. And then we set a random state. So every time we run this, it'll give us the same split. So let's go ahead and do that. And then we'll set up our predictors. So as we saw in the animation, we'll be using athletes and events as predictors. And our target will be medals. So this will be what we're predicting. So we can go ahead and split our data up. And we will create our X matrix, which is just our train predictors. And then we'll create our Y matrix, which is going to be our target. And we'll copy both of these because we want to avoid a pandas setting with copy warning. So copying both of these avoids that warning. So let's take a look at X, and we can see X is now 1,611 rows, and we can see we have our athletes and events columns. We can take a look at Y, and we see this is our medals. The next thing we need to do is scale our X values. So we will go ahead and find an X mean and an X standard deviation. So we will calculate those. So for each column, this will calculate the mean and the standard deviation, as you can see here. So X mean. And then we will actually scale our data using these values. So we will go ahead and subtract X mean from X, and then we will divide by X standard deviation. So what this will give us, if we look at x.describe, is it will ensure that our mean is 0. So ignore the weird numbers here. So this is just a really, really small number, which is why it has the negative e to the negative 18, which means move the decimal point 18 places to the left. So NumPy sometimes has issues with floating point precision, and sometimes a 0 will show up as just a really, really small number. So these are zeros, and this is a 1. So we've rescaled our standard deviation to 1 and our mean to 0. Now we can go ahead and add an intercept term into our X matrix, and this is necessary for us to calculate the y-intercept coefficient. And then what we'll say is x equals x-intercept plus predictors. So we put our intercept value first in our matrix. So we can see that we now have our intercept column first, then athletes, then events. So intercept will be B0, athletes will be B1, events will be B2 in our coefficients. All right, now we can take a look at X transpose just so you see what it looks like. So before intercept, athletes, and events were our column headers. Now they are our row headers, or row indices rather. So the matrix has been turned. That's what the transpose is. Now we can calculate our penalty matrix. So let's set alpha to 2. And I'm going to call lambda alpha now because there is already something called lambda in Python. Lambda is actually the keyword to define an anonymous function. So we can't actually call a variable lambda. So I'm going to call it alpha instead. So just know what we called lambda in the animations, I'm actually just going to call alpha now. All right. Now what we can do is create the identity matrix. All right, so that's our identity matrix I. So you can see it has 1s in the diagonals. And what we'll need to do is actually set this top left value to 0. So I'll go ahead and just say I00 equals 0. So let's take a look at our identity matrix again. And this is now a 0, which, as you'll remember, we need because we don't want to penalize the y-intercept. Okay, now we can create our penalty matrix by multiplying alpha by I. So take a look at penalty, and we can see this is now our penalty matrix. Now we can actually implement the equation to solve for B. So if you remember, that inner part of the equation is x dot t, so x transpose, times x. And I'm using this at symbol here for matrix multiplication. So you can't use the normal multiplication sign. Matrix multiplication works differently from normal multiplication. And if you check out that linear regression video in the description, you'll see how matrix multiplication works for linear regression. And then what we do is we add the penalty matrix to this, and we take the inverse of all of it. All right, so that's how that looks. And then to finish calculating our linear regression coefficients, we then multiply this by xt and multiply by y. So this will give us our full ridge regression coefficients. So this is our y-intercept, 10.69. This is our B1 value for athletes, 61.85. And this is our B2 value for events, negative 34.6. And to make that more clear, we can add row labels into this data frame. So we can now take a look at B, and we can see which coefficient corresponds to what. All right. Now we can use our coefficients to actually make predictions. So we have to do the same thing with our test set that we did with our train set. So what we'll do is we'll say test x equals test predictors. So that's creating our same x matrix, but for our test set, which is that 20% of the data that we reserved to evaluate our model. Then we'll do the same thing where we scale our test set. And you'll notice I'm doing the scaling based on the mean and standard deviation of the training set. And the reason I'm doing that is when you train a machine learning algorithm, you usually don't know the data you'll be using to make predictions on when you're actually doing the training. So that's why I split up the sets and then found the mean and standard deviation of the train set, and then I'm scaling the test data using the same mean and standard deviation. It's so that everything aligns with how we would actually use this in the real world. Okay, so then we'll say test x intercept equals 1. This is exactly what we did before. And then we will go ahead and reorder our columns. So intercept plus predictors. All right. Now we can take a look at our test x, and we can see it looks very similar to our training data, except it only has 403 rows because we took 20% of our data for the test set. We can see we have an intercept, athletes, and events column. Then all we need to do to calculate our predictions is to say test x multiplied by b, and that gives us our predictions. So this is the predicted number of medals that we predict each country to win based off of our ridge regression model. Now what we can do is we can compare our model to the scikit-learn implementation of linear regression, just to see if it matches that implementation. So from scikit-learn.linear model, we can import ridge, and then we can initialize our ridge regression algorithm with the right alpha parameter. And then what we'll call is ridge.fit x predictors and y. We don't need to pass our intercept term into the scikit-learn ridge model because it'll actually add the term on its own. Okay, and then what we can do is check out the coefficients, and we can check out the intercept term. And what we see is the intercept is 10.69. The athlete's coefficient B1 is 61.85, and the B2 coefficient for events is negative 34.63. Let's make sure this matches our model, and it does. So we know that we actually implemented this correctly, which is great. Then we can just make sure our predictions match the scikit-learn predictions. So we'll call predict on our scikit-learn regression model, and we'll pass in our test x predictors. And then what we can do is say predictions minus sklearn predictions, just to see what the difference is, if any. And we again get this very, very small value that is 0. There's just a NumPy precision error here, or precision issue here. So this is 0. So we can see that our predictions are identical to the scikit-learn predictions, which is fantastic. All right, now the last thing we can do is determine how to find the optimal alpha. And in order to do that, we are going to wrap what we already did up into functions. So I'm not going to type all of the code out again. Instead, I'll just copy paste and I will explain what's going on. So this is the exact same code we just wrote. And what this does is it's first generating our X and Y matrices from our training data. Then it's finding the mean and standard deviation. Then it's actually correcting our data, so scaling our data so that the mean is 0 and the standard deviation is 1, then adding in the intercept, then calculating the penalty matrix, and then finally running the full equation to get the coefficients. So this whole thing is just fitting a ridge regression model, doing exactly what we did before, nothing's different. Then we can write another function called ridge predict, which will take in our test set, our predictors, x mean, x standard deviation, and our coefficients b. And I'll again copy and paste the code here because it's the exact same code we just wrote. But what we're doing is we're creating our X matrix for our test data. Then we're scaling that data, standardizing that data. Then we're setting the intercept to 1, and then we are generating our predictions. All right. And we're going to use these two functions to actually find the optimum alpha parameter. So we're going to import another utility function from scikit-learn called mean absolute error. And what this will do is tell us how good our model was. It'll tell us the difference between the actual y values and our predicted y values. So it'll help us judge if our model was good or not. And basically what we're going to do is we're going to test a bunch of different alphas and see what the error is on our test set. And we'll pick the alpha where the error is lowest. So we'll create a list called errors to hold our error values. And then we'll initialize a list called alphas that's going to contain all of our alpha values. Okay, and I generated a few alpha values here. So going from 0.01 all the way to 1,000. You can definitely try different alpha values if you want to experiment a bit. And then we can just write a loop for alpha in alphas. A little typo there. What we say is b x mean x std equals ridge fit. We pass in our training set. We pass in our predictors, our target, and our alpha. So this is calling that function we just wrote that will fit a ridge regression model. Then we're going to generate predictions using the function we wrote called ridge predict. We pass in our predictors. We pass in our x mean, x std, and our b coefficients. Then to our errors list, we're going to append mean absolute error. And we will find the error between our actual test values, which are test target, and our predictions. Okay, I did ridge ft instead of ridge fit. Gotta love the typos. So let's take a look at errors now. And at each alpha value, this is the corresponding error. And we can just display our alphas list here. So this is the error for an alpha of 0.01. This is the error for an alpha of 0.1, 1, and 10. And we can see 10 is the alpha that gives us the lowest mean absolute error. So this helps us decide what the best alpha value is. And you can see error goes up as we increase our alpha. So I was talking about underfitting versus overfitting. Here's where we're overfitting, and here's where we start underfitting, and our error starts going up again. So you want to pick the alpha where the error is the lowest, but if you set your alpha too high, your error is going to go up due to underfitting. All right, we did a lot today. We covered the theory behind ridge regression. We talked about the equation. We went ahead and implemented it in Python, and then we determined how we can evaluate our model and find an optimum alpha. I hope you enjoyed this video, and thanks for watching.